Hi everyone, we're going to look at Unit 2, Lesson 5. So far this unit we've looked at logarithmic expressions and evaluating them, converting them to exponential form. We have graphed logarithms. We learned about our log rules. And so in this lesson, we are actually learning how to use what we know about logarithms to solve exponential equations. So at the top here, we have a little section of recalling some things from the past. So log base 4 of 16,384. So I need to think to myself, well, 4 to what exponent would give me 16,384? So in my calculator, let me grab it. I can do like 4 to the power of 3. Well, that's not what I want. I got 64. Sorry, my lighting is a little weird. 4 to the power of 4. Nope. 4 to the power of 5. 4 to the power of 6. 4 to the power of 7. Ooh, so 4 to the power of 7 gives me 16,384, which means log base 4 of 16,384 is equal to 7. So that's kind of how we think about it. But then we also can use our math button on our calculator. So math is here under alpha. I can click that. And then pretty far down, I have log base, and I can just type this in. So log base 4 of the 16,384 gives me 7. So this one here, if I don't have a base, I do have an invisible base 10. So 10 to the power of what gives me 100? That would be 2. And then for this one, my base matches the base that has the exponent on it. So both are f's. And so here, because they match, my answer would be whatever my exponent is. So log base f of f to the third is just 3. And so if I do my cloud, f to the power of 3 gives me f to the power of 3. So then for number 4, 5, and 6, we're actually converting the exponential equation to logarithmic. So I'm going to use this one as an example for us. This is the logarithmic equation. If we convert it to exponential, it would be 4 to the power of 7 equals 16,384. So I'm going to use that to help me here. So the base that has the exponent on it is the base of my log. So log base 10. And technically, I don't have to write the base 10 because if it's invisible, it is understood, just like in number 2. And then the argument of my log, so in this one, the argument was that large number, is going to be whatever the exponential is equal to. So here, my argument would be 1,000. And it's going to equal my exponent, and my exponent was x. And so I can double check if I do my cloud, 10 to the power of x gives me 1,000, 10 to the power of x equals 1,000. So I want to make sure they're in the right place. This one, my base that has the exponent on it is 9, so the base of my log is 9. My argument is 180, and it's going to equal my exponent of x plus 1. I double check with my cloud, 9 to the power of x plus 1 equals 180. One thing I kind of remind myself is if 9 and 180 are really close in the log, they're not going to be really close in my exponential. 9 is over here, 180 is on the other side. Same thing, 9 is really close to x plus 1. They're not going to be close in my logarithmic. So here I would have log base 2 of 64 is equal to 3x minus 7, and I can check with my cloud. Underneath, there's a couple questions in the Jumpstart. I want you to take a couple seconds to pause the video and answer both questions, and then you can restart the video, and then we'll be on to the back. All right, so we're going to look at solving exponential equations today. So first, we want to make sure we understand what an exponential equation is. So an exponential equation is one in which the variable occurs in the exponent. So looking at these three examples here, all three of these are exponential equations. My exponent has the variable. My exponent has the variable. This one, both of my exponents have a variable. And all three of these are going to be something that we could learn how to solve. I want you to create a different exponential equation in this box, and then we're going to look at how we attack these problems. So here it says find the solution of each of the following equations and round to 4 decimal places if necessary. So we're going to go through the steps first, and we're going to apply those steps when we solve the equations. So the first thing that we want to do is we want to isolate the exponential expression on each side of the equation. So isolate just means that we want to get it alone. And so I'm going to talk about these three up here real quick. This is where my exponent is as my variable. I'm looking at if this is isolated. There's nothing being like added or subtracted onto my 3 to the power of x, so this would already be considered isolated. Here I find my variable, it's in my exponent. This is the term that I want isolated. Right now it's not, because I still have this plus 2, so I would first have to move the 2 and then I would have it isolated. And this last example, my exponent that has a variable is in this term and in this term. Now it does say in step 1 on each side of the equation, and so this would be considered isolated. There's nothing being like added or subtracted on the outside or being multiplied onto the outside of that. So this would already be isolated for step 1. So step 2 is once we have it isolated, we want to think about the inverse of an exponential. Since these are all exponential equations, the inverse of an exponential is a logarithm. So we're going to take the logarithm of both sides, or of each side of the equation, and then we can use our laws of logarithms to bring down our exponent. And I'll show you what that means when we go through an example. And then the last step is we want to use inverse operations to solve for the variable. So if we notice addition, we would use subtraction. If there's multiplication, you use division, that sort of thing. So looking at number 1, we have 3 to the power of x minus 1 equals 19. So for step 1, I want to isolate the exponential expression. So looking here, I have my variable connected to a base of 3, so this is what I'm looking to get isolated. As of right now, it is by itself, and so step 1 is already done. So I'm going to make a little note. It is already isolated, and we can move on to step 2. So for step 2, we want to take the log of both sides of our equation. So I'm going to take the log of this, so I would have log of 3 to the power of x minus 1, and then whatever I do to one side, I also have to do to the other side. So log of 19. Notice I'm using a common base 10, and I didn't write it. Now that I took the log of both sides, I want to bring down my exponent. So one of my log rules is if I have an exponent on my argument, I can bring it down as a coefficient, and I'm going to do that. Now for this exponent, I have x minus 1, and so I want to make sure I put that inside parentheses. So out in front, I have x minus 1, and it's getting multiplied onto log of 3. So I just brought down my exponent. On the right side of my equation, I don't have an exponent to bring down, so I just keep it as log of 19. So now that I have no exponents, I want to use my inverse operations to solve. So this is moving on to step 3. One thing I want to point out is if I have log of 3, this is just a number. Same thing with log of 19. This is also just a number. And so if I want to try to solve for x, I have to get rid of log of 3. To do that, I'm going to divide the entire side by log 3 so that these cancel. If I divide the left side by log of 3, I also have to divide the right side by log of 3. So on the right side of my equation, these cancel. I'm left with x minus 1. And then log of 19 divided by log of 3, we're definitely going to use our calculator. So in my calculator, since it's a common base 10, I'm going to use my log button that's next to my number 7. So log of 19, make sure to close your parentheses after the 19, and then divided by log of 3. And I get this decimal. So I'm going to round it to about 5 decimal places for now, and then I'll make sure that my final answer is rounded to 4 decimal places. So I have 2.68014. The longer we can keep the log of a number instead of the decimal version, the more accurate our answer will be. So now what I have is like a normal equation that we're used to solving, where we have a variable we want to get alone. I don't have any more logs to take care of. And so to get x by itself, I just want to do the inverse of minus 1. So I add 1 onto both sides. Those will cancel, and I'll be left with x equals 3.6801. And I did 4 decimal places because that's what the instructions asked for. And this is my answer. And we solved our first exponential equation. So let's look at number 2. I'm going to scoot this just a little bit so we have more room. So number 2, I'm going to start the same way. I want to isolate my exponential expression. So my exponent with the variable is connected to the 2. So this needs to be isolated. And I notice that I have a times 5 here. So I want to get rid of that. So I'm going to divide this whole side by 5, divide this whole side by 5. These 5s will cancel, and I'm left with 2 to the power of z plus 1 equals, well, 30 divided by 5 is 6. Now I want to double check, is my exponential expression isolated? It is, because there's nothing left on the outside of that. So now that it's isolated, I move on to step 2. I want to take the logarithm of both sides. I'm going to make it look a little different this time. So I'm going to do log of that and log of that. Whatever I do to one side, I have to do to the other. So when I write it prettier, I have log of 2 to the power of z plus 1 equals log of 6. I'm still using common base 10. Now that I have the logarithm on both sides, I can then bring down my exponent. That's one of my log rules. Again, I want to make sure this is in parentheses when I bring it down because I have 2 terms there in my exponent. So I have z plus 1, and that's my coefficient on log of 2, so it's being multiplied onto log of 2, and it still equals log of 6. Now I want to try to solve for z, so I first have to get rid of this log of 2 because that's just a singular number. I know it looks like 2 separate things, but this is just one thing. So I'm going to divide by log of 2, divide by log of 2. These will cancel on the left-hand side. And I'm going to figure out what this is in my calculator. So I have log of 6, close my parentheses, divided by log of 2. And I get about 2.585 because the 6 would round the 9 up. So I have z plus 1 equals 2.5850. I'm just going to show that again. So then to get z by itself, I subtract 1 on both sides, and we get z equals 1.5850. The main thing to remember is to use our steps. And then we're still doing inverse operations like we would for any equation. We know the inverse of exponential or exponents is logs. That's why we take the log of both sides. And then from there, the inverse of multiplication is division. The inverse of addition is subtraction. So for the last one on this page, you notice it looks a little different. This time I have two exponents on each side of my equal sign, and they both contain a variable. And that's okay. I still want to follow my steps. So the first thing I'm going to do is I want to isolate my exponential expression. So here, this exponent is connected to 5. This needs to be by itself. And it is. This is just question 3, so that's separate. There's nothing else connected to that. And then here I have another variable connected to this 5, and that is already isolated as well. So step 1 is done. They're already isolated. So we move on to step 2. I want to take log of both sides. So I would have log of the left, so log of 5 to the power of negative g. And then I also want to take log of the right side, so log of 5 to the power of 3g minus 2. Now that I have logs on both sides, I can use my law of logarithms to bring down my exponents, bring down that negative g, and I'm going to bring down the expression 3g minus 2. Remember, I want them in parentheses. So we have negative g out in front of log of 5. Since it moved down, there's no longer an exponent there. And then here, I'm going to put that in parentheses, 3g minus 2, and that comes in front of log of 5. I actually think this is nicer because something I notice is if I want to get rid of log of 5, I'm going to divide by log of 5 on both sides. But here, log of 5 divided by log of 5, those cancel. On the right-hand side, log of 5 divided by log of 5 also cancels. And that's really nice. So now I just have negative g on the left. And then on the right-hand side, I have 3g minus 2. I don't have any decimals right now, so I can go ahead and solve this like a normal equation. I want to get all my variables onto one side, so I'm going to subtract 3g. So I have negative 4g equals negative 2 because those canceled. I want to get g by itself, so I'm going to divide by negative 4. My negative 4's cancel on the left. So I have g equals, this will turn into 1/2, or it would be 0.5 as a decimal. I realize you can't see that. And so this is our final answer. So we looked at kind of one example from each scenario. We did one where there were variables on both sides. We did one where it was not isolated yet, and we had to get rid of that 5 first. And then we did one that was already isolated with just 1 on the side. So now we're going to look at the last page. So go ahead and flip to the next slide. So here we have a system. So it says find the solution of each of the following equations, round to 4 decimal places. This first one here, if I have 2 equations and they both are equal to y, I want to solve it by substitution. So what that means is if y equals 100,000, this 100,000 is going to go in place of y, and I can rewrite my equation as 100,000 is equal to 10 to the power of 3x plus 1. I can also think about it as if they both equal y, I set them equal to each other. So I take my 100,000 and I set it equal to the 10 to the power of 3x plus 1. So from here, the reason that I'm not using my graphing calculator for this is if I put in 100,000, that's such a large number that I would have to zoom out so far, I wouldn't be able to see this in my graphing calculator. And so when I set this up, I actually noticed that it looks similar to the ones that we just did in questions 1, 2, and 3. They just weren't as big numbers, but I can approach it the same way. So I want to look at where my variable is. It's connected to the 10. Is this isolated? It is, because this plus 1 is in the exponent. So this is already isolated. I can go ahead and take log of both sides. So I'm going to take log of each side. So I have log of 100,000 and then log of 10 to the power of 3x plus 1. I can bring down my exponent in front of my log. So I have log of 100,000 equals 3x plus 1 times log of 10. So here I want to get my variable by itself, but it's in these parentheses, so I have to get rid of log of 10 first. So I'm going to divide both sides by log of 10. Log of 10 divided by log of 10 cancels, so I want to do this in my calculator. So I have log of 100,000 divided by log of 10, and I get 5. So I have 5 is equal to 3x plus 1, and then I can solve this. I subtract 1 on both sides, so I get 4 equals 3x, divide by 3, and I get x equals 4/3, which is the same thing as like 1.3 repeating. 4 decimal places would be rounded. Now, if I look at the next ones, I have an exponential for one equation because my variable's in the exponent. And my other equation also has a variable, but it's just a linear function. So I have to approach 5 and 6 differently. For this, I want to utilize my graphing calculator because it is a tool that will make it so much easier. So the first thing that we're going to do is we're going to input our functions. So we're going to type each equation into our graphing calculator. Using the y equals button. So I'm going to fill in the next step and then we'll do it together. Once I have them in my graphing calculator, I want to click second trace so I can calculate where they intersect, and I want to choose option 5, which is labeled as intersect. Because if I'm looking for the solution to a system, which is just multiple equations, that is where they intersect. I'm looking for where they cross, where they intersect, where they touch. That's what a solution to a system is. So for number 5, I'm going to take my graphing calculator, and in my y equals button, the lighting is kind of weird here, I hit y equals, and I'm going to type in my 2 equations. So the first one is 10 to the power of 2x. And remember, for our variables, we use the xt theta n, the button underneath mode. And then the plus 1 is not in the exponent, so I'm going to hit my right arrow and then do plus 1. I want to make sure it looks identical to the one I'm given. Then to type in my second equation, I'm going to hit my down arrow, and in my y2, I'm going to type in the second equation, so negative 4x plus 1. Make sure I have them both in. They look identical to what I'm given. So we did step 1. We input our equations into our graphing calculator. Now let's just look at what the graph looks like. So I'm going to hit my graph button. So that's my first equation, the exponential equation. And then the second equation is that linear one. So they do cross somewhere there. I need to figure out what that point is. So I'm going to click second trace. And I'm doing second trace because I want calc. I'm going to calculate where they intersect. So second trace, and I want option 5. for intersect. I'm going to hit enter. And so my calculator says first curve. And I notice that I have a blinking, it's called a spider. And I just want to make sure it's on the first curve. So I'm going to use my left and right arrows, and I'm on my exponential. So I'm just going to hit enter. And then for second curve, I just want to make sure it's on the linear function so that each time it's on a different graph. It already is, so I'm just going to hit enter. And then it says guess. So I'm going to use my arrows and try to move that blinking spider as close as I can to where I think the intersection is, and go ahead and hit enter. And so it tells me my intersection point. I have the X value of the point and the Y value of the point. And then I can write it as my answer. So for number 5, I know that these two intersect at an X value of negative 0.1345, because I want 4 decimal places again. And the Y value is 1.5382, because the 6 rounds the 1 up. And I'm done. That's what I need to do. So I want you to try number 6 using those same steps, and then you can pause the video, and then you can restart it to see if you got the same thing as me. All right, so let's see what we get here. I have negative 3 to the power of 4x minus 2. Don't forget that negative out in front. And then my second one, 2x minus 5. I'm going to check what my graph looks like. Just thinking. All right, so it looks like they intersect about there. So I'm going to do second trace. I want option 5. First curve, I'm just going to hit enter. Second curve, enter. And I'm not even going to move my cursor this time, and I'm just going to hit enter and see what happens. And it still gives me the intersection point. So I really just hit enter, enter, enter. So the X value is 0.7810, and my Y value is negative 3.4380, because that would round. And that's our solution. And we did it.